This video is only for separate science students and contains some of the trickiest parts about forces. One of those things is something called a moment. Now, a moment is a turning effect of a force. Now, anything that turns, like a door handle or an axe or a spanner, will be an example of a moment. We can calculate it using the equation moment equals force multiplied by distance, but not just distance, it is the perpendicular distance from the line of action of a force to a pivot. I'll explain what that means in a second with a diagram. Effectively, it will almost always be just regular distance, but there is an important distinction. So let's say this block here, the line of action is the line going downwards. That's the weight of the block. Now, the distance between the block and the pivot is the distance that we're talking about in the equation. Now, perpendicular just means at right angles to the force, so they are 90 degrees to each other. Now, the units, force is newtons, distance has always got to be in meters, moments therefore are measured in Newton meters. A moment is an example of a vector, so that means it has a direction. Now, the two directions it can be in are either clockwise or anti-clockwise. Okay, so clockwise, like 12, 1, 2, 3, 4 on a clock, or the opposite direction, because it's always turning. It's never just left or right or back or forth. Now, let's say we go back to our seesaw and we have a look at this situation in a bit more detail. Now, lots of moments questions, especially mathematical ones, will involve something being in equilibrium. Okay, equilibrium, we should know from my other forces video, means things are balanced, basically. Okay, now, particular for a turning force, equilibrium doesn't just apply to forces; it applies to moments. And equilibrium means that moments clockwise are equal to moments anti-clockwise. Notice I've said moments there. It could be more than one, doesn't have to be, but they all have to equal each other on each side. So let's have a look at what that means then for our example. So let's say I've got F force and D for distance on this side. I'm going to call it F and D1 just to distinguish it from the other side. On the other side of my pivot, I've got F2, the force going down, and I've got another distance, D2. So what this equation means is that if I multiply F1, force 1, times the distance 1, it would equal the other side. So that will equal F2 times by D2. So the clockwise moments equal the anti-clockwise moments on my diagram. Let's make some numbers in there just to see how we would solve these kinds of equations. So let's say F1 is now 120 newtons and F2 is 90. And usually in an equation like this, they'll give you one of the distances and you might be asked to work out the other. It can get a bit more complex than this, but this is the basics of it. Okay, so using our equation, we're gonna, there we go. So 1 meter for the D2 distance, and we're trying to find what D1 is. So let's put in our numbers, just like we normally would do with FIFA. So we'd say the moment going clockwise is 120 newtons times by, we don't know, D1. The other way is 90 times 1. So what I then do is rearrange this whole equation for D1, and then maths is relatively straightforward in this equation. It's 90 divided by 120, which happens to equal 0.75, which makes sense because the closer you are, the higher your force has to be to make the same moment. My diagram is not to scale. Now, moments are an example of what's called a force multiplier. So a force multiplier essentially increases the effect of a force. So you put a little bit of force in. If you apply it at a certain distance, you can get a lot of force out. This is used in spanners, in crowbars, in lots of different things. You're trying to lift up a heavy block. You use a crowbar because you have a higher distance. You're increasing the distance, therefore you're increasing the moment, even though you're not applying any more force. The whole point is to make the effect of your force bigger. Now, something else that is also a force multiplier are gears. So gears, we should know where you might find them, so on cars, bikes, etc. And they are force multipliers in a slightly different way. Now, don't get too hung up on gears. There's very few things you could be asked about them, really, in terms of what they do. And it's only come up once in the last few years on separate science papers. So it could be factory machines as well as bikes and cars. So what gears do is they transmit a rotational force or rotational forces. So what that means is transmit from one gear to another forces, but in a turning or rotational motion. Okay, so let's say the first gear on your bike, the chain is able to transmit that force to the rear axle to enable the wheel to move. Now, there's two situations you might use a gear. You might go from a small to a large gear, so that will be going right to left on my diagram. Now, the purpose of that is to go into a larger gear, has a bigger radius. The idea is it increases the force out of the gear and decreases the speed. So for example, on your bike, you would want that kind of thing when you're going uphill because you're traveling against gravity and you don't need to go fast, you just need to go up the hill. The other situation would be if you go from a large to a small gear. Now for that situation, the force that you get out is going to be a lot smaller, but you're going to be traveling a lot faster because the gear is smaller. So that situation would be if you're going downhill. You don't need to have a high force because you're already going downhill, but if you want to go for a lot faster than you were initially. And that's it for gears. Now let's look at center of mass and stability. Okay, so center of mass for regular shapes such as triangles, squares, rectangles, etc. You can find by doing either lines of symmetry or just from going corner to corner. I haven't done a very good example there. And the center of mass is in the middle. Now it doesn't have to be in the shape. For a donut shape, the center of mass would still be in the middle even though there's none of the shape there. To define the center of mass, we say it's the point at which all the mass of an object can be considered to act or thought to act. Okay, so it's not like all the mass of the object is there, but when we are doing calculations, we can consider it to act at that point. Now, it always lies below, on the line of action, below a point of suspension of an object. Let me show what I mean with a diagram. So if you were to hang up an object just from a pin or something like that, the center of mass will always lie directly below the point at which it's suspended from on the line of action. Now, you might remember doing this in a practical. If you've got an irregular shape, this still applies. So one of the ways of finding the center of mass is to do this multiple times from multiple directions, and all the lines will cross over, and the center of mass will be in the center of those lines. How do we apply this then? So for stability, for objects to become stable, they need two things. They need a wide base and a low or lower center of mass. So a wide base, we've got two examples here. These are two double-decker buses that are going around a bend at an angle. Let's say for the first one, the center of mass is low. You can see how, if I draw a line of action, the line of action is within the wheel base, so it will be stable. With a high center of mass, lots of passengers on the top, is outside the base. So therefore, it will become unstable or unstable. Now, how we describe this is we say the line of action lies outside the base, so there is a resultant moment. Really good phrase to use if you're talking about things turning, a resultant moment.